Welcome back. So this is the inside cover from my book that I wrote about 2020, I think it was, a few years back now, called Feedback by Tom Moyer. It's quite a big book, quite comprehensive. And in it, I cover most of the things in undergraduate control systems. Usual step responses and transfer functions and frequency response and board diagrams and feedback and state space and some other things as well. Nonlinear control. So I was just thinking, normally when you're a student or an engineer, you use tools to plot things like frequency responses nowadays, and you use things like Matlab to help you with the modeling, or if you want to, you can write your own software, but not many people do. I mean, we used to in the old days have to write everything ourselves in Fortran. But I just wondered if AI could do this without the need. I know that in AI, and I've showed you how to do this, you can get AI to produce MATLAB code, and then you can run MATLAB code. But is there a need for this? Can we bypass the step where you need the code and just get it to do it straight off? So I asked myself that question. And just before I do that, I'll just explain what I'm trying to do here. I picked an example of, I wouldn't say frequency response, but a bit like frequency response. It's a 3D frequency response. This is the standard thing you'll see in most textbooks, the S-plane. If you've got poles on the S-plane, if they're complex, of course they come in pairs. If they're real, here, if everything in the left half plane is stable, the right half plane is unstable, and right on the axis it's an oscillator. If you've got poles, and again they come in pairs there. This is sigma and the real part of S, and j omega, the imaginary part of S. This is the normal symbols that we use. Usually we either show the S-plane or the frequency response, which I haven't got here, but I'll just go on to show where it comes from. So if I keep going, it's not there. Biggest problem is finding out where it is. It'd be further back. Yeah. So here I've got a transfer function, g of s, so it's 1 over s squared plus s plus 0.5. That could, I don't know what that could be off a motor, part of a motor transfer function. You can plot this in 3D, which is not something we do a lot. You do see it in some textbooks, but I found it more illuminating to look at the 3D plot. And we never did this when we were students because we didn't have anything to plot 3D graphs with. But ever since the late 70s and early 80s and so on, when we can plot 3D graphs, on basic computers, it's become something that's a bit more interesting. So what we do with these 3D plots is we substitute s equals sigma plus j omega, and so there's our sigma and j omega, and we plot the magnitude of that, because remember, it's just a complex number. That's all it is, with different values of sigma and different values of j omega over a range. And here we've plotted it from -1 to +1 for sigma and omega. And if you do that, you get this, because there's two poles, and then they're stable poles. They're going to be at -0.5 plus or minus something or other, but in the left half plane nevertheless. If you're looking down on this 3D graph here, you can see that the poles, so just imagine you're on an aircraft flying along here and you're looking down on this 3D graph. You'll see, you won't be able to, if you were vertically above these, you wouldn't actually see these are mountains. All you'd see is what we denote them here is with crosses, just like I showed you on the S-plane. So looking from the sky, if you like, these poles just look like crosses, but if you're looking from the side, they're like mountains, and that's why they're called poles, because they go up to infinity like a pole. But they only happen at that particular complex frequency, which is called the poles of the system, which are in complex conjugate pairs, of course. For a linear system here, you can't get anything else. If it's complex, it's got to be in a pair. Not aware of anything else anyway. If it's real, then there would just be one pole on its own. And zeros, there's no zeros there, would be like a hole in the ground, like a pothole almost. So if you're wondering, so the S-plane comes from this 3D plot rather. So the S-plane, so looking down on there is the S-plane, and we don't, as you can imagine, we don't use negative frequencies usually in control systems. I know in signal processing we do, when we do FFTs and so on, but even there we kind of get rid of them normally, eventually. So we're really only interested in a slice through here, and the way it's been drawn here is that the positive frequencies are going in that direction rather than that direction, but never mind. But if you can imagine the front of this, is if this was like a I don't know what you call it, like a thing for a fish tank, and you followed the contour of this graph from here to here, and just in this plane here, then you would you would actually see the frequency response, and it doesn't go to infinity because we're not going deep into here. We're not plotting it along from sigma is minus 0.5. We're plotting it down here at this point here. So if, for example, there was a pole on the j omega axis, then it would go to infinity, and that's exactly what you get with an oscillator. You get this magnitude that shoots up to infinity. But for all other complex systems, the system can be stable unless you excite it exactly at the pole, which means you have to put a complex frequency in at that, at the right place to excite it to go to infinity. So the system is nevertheless stable because its poles are on the left half plane. But just to try and explain to you as much as I can on this, just with a cursor, that the Bode plot is like the front of the plane here, whereas the S plane is looking down on the top. Okay, so there it is, drawn like that. I didn't draw the magnitude. So getting back to AI, I started off on Copilot, and it didn't give me very good answers. I just said to it, I just thought I'd get it to do a simple graph. Draw the graph of y equals x squared. We can't get much simpler than that. When I did it, I didn't get anything sensible out of it at all. I remember this is using, it's got a graphical output, which is nice. DALL-E 3, it's got really nice graphical output. So it's great for doing images, but can it do maths? So is Mrs. Microsoft Copilot? No, because it just comes up with rubbish. So, I mean, these are really cool graphs, I think you'll have to admit. But it doesn't seem to be anything to do with y equals x squared. Plus the fact it's a 3D graph it's drawn, I didn't ask for that. I mean, if I'd asked it to do 2D, I don't think it's going to make any difference. Draw the 2D x, y graph of y equals x squared. See if that's any difference, any better. Of course, the question here, can you plot y equals 2x minus 3? I doubt it can do that, but I guess we could try that as well. Again, it's plotting 3D graphs, which seem to be totally unrelated. It's got a nice imagination. Notice how it can't get the axis on the graph either, because like a lot of the, DALL-E has difficulty with text. So it can't really do that. So we can forget that. So I moved on to ChatGPT. So I moved on to ChatGPT. I eventually got it open. For some reason, it wouldn't let me in to begin with. And this is a history of what I did. So I started off, I went into Math Solver, though not the basic ChatGPT. And I believe I'm using ChatGPT 4, so I'm not subscribed to it. So it does bomb you out after a few goes. And I just asked it to do y equals x squared, and it does a lovely y equals x squared. you can't really complain about that. But of course there are other programs on the internet that will plot your graphs like that, so that's not such a big deal. So then I moved on and I said, for a transfer function with a Laplace transform, g of s is 1 over s plus 1, so it's first order. That should be if rather than is. If s is sigma plus I omega, where I is the complex variable square root of -1. I know in engineers we normally call it j, but I put it as I. Draw a 3D graph of magnitude of g of s versus sigma and omega, and no problem at all. Because it's got built-in graphics, it plotted me the 3D graph. Similar to the book, this is a first order example, however. And again, looking down from, you can see it's only got one pole at -1. Which is there. Looking down from, an aircraft, an aerial view, you just see like the cross there is the S-plane, and it's just one pole at -1. So the real axis is along here, and that's the imaginary axis this way. This way down the center, that's j omega. If you want the frequency response, it's down the center. It's there's no resonance, but I know there's a resonance there, but that's at a complex frequency, so you don't see that because you're operating here, and so you don't see any overshoot in the frequency response. It's pretty flat actually, and although you can't see it, it just goes down, rolls down like a typical first order system. Now to see it a bit better than that, pick a more difficult example. It explains to you though about it, how it did it, which is really good. And so it hasn't used Matlab or anything like that. It's just did it itself. So I've just said repeat the previous question, but like g of s is s plus 1 over s squared minus s plus 1. That's an unstable system. It doesn't matter though. If you can still theoretically work out its frequency response or its draw the poles and the zeros. It's obviously got 1 0 at -1 and 2 poles, which are, if you solve that quadratic, it's 1 plus or minus square root of 1 minus 4 over 2. So it's a 0.5 plus or minus something or other. It's in the right half plane. And so it's got 2 poles and 1 0. Just look at the 0 first. The 0 is at -1. It's very hard to see here, the 0. By the way, you can pull that off, which is quite handy. Put it on the desktop. There is a dip down there. If you were walking along there, like there's a piece of carpet, walking along the S-plane, then you drop down a hole there, going to -infinity. So it's like a black hole. I wouldn't recommend walking around there. If you're ever on the S-plane, don't go in these zeros, because they'll pull you in. Whereas the poles are these mountains that go up. This is just a graphical thing that they're not the same height, numerical thing rather. And so those are the complex poles. So if you're looking down, again, you're going to see 2 complex poles. The cross is in the right-hand side. The frequency response is, so here's omega. It's going to be here again. So you don't actually see much. It's along there. This vertical, the vertical axis is the magnitude, and this axis here, I think it is the frequency along here. And it won't go to infinity again because the poles are in the right half plane. They're not on the j omega axis. Okay. And then I went to see if it could do the step response of 1 upon s plus 1, and I run out of data. I run out of time. It says I can't do it, and to come back in 12 hours. It says, which isn't really much good. So I thought that was good because that's actually bypassing Matlab altogether. I mean, it's nice to have all these tools, but if you've got the money for them, you can buy as many tools as you like and swap about. But wouldn't it be nice to just have this one super brain that can do all the graphing and work out the calculations and do everything to help you? Let's do something on Claude. Now, Claude is supposed to be even better actually than ChatGPT for mathematical things, but it doesn't have graphics built into it as far as I know, at least not this version. So if I do find the unit step response of the transfer function g of s equals 1 over s plus 1. Now that's a standard first order with a time constant of 1, tau if you like, and it let's just see what it does. So it tells you mathematically, well, it's quite good. It even gives you the Laplace for it and the partial fraction expansion, and it gives you the answer 1 minus e to the minus t. And if I ask it to draw that, repeat the previous prompt, but plot the result on a 2D graph, it should be able to do that. It's basically saying if you want to plot it, mate, I can't do it, but you can do it this way if you've got Matlab. So, and that's fine. I mean, if you've got Matlab, you can do that, or you can do something similar in Python. You could ask it to do a Python program, but again, is what I'm asking here is there really a need to do that? You know, if we've got proper AI, we should be able to bypass these other tools as well and just ask everything in language. Of course, you've got to really understand and state your problem very clearly, because if you ask the wrong question, you'll get rubbish in, rubbish out, as they say. So there it is. If you've got ChatGPT 4, the full version, maybe you can give it a go yourself and tell me how you got on. But it may be that in the not so distant future, unless these other programs keep up, like Matlab, that we might not need to use them as much, because the AI will be able to kind of do a lot of the mathematics itself within the AI algorithm. You've got to be careful, of course, because some AI algorithms are not good for some things. I mean, for example, ChatGPT, if you have a look online, you'll see it certainly the earlier version, I'm not sure ChatGPT 4, but the earlier version was pretty useless at chess, and it actually started to cheat. If you had any chance of winning, it would start to spawn rooks and things, and it didn't seem to understand the game properly, because again, it's not trained as a chess program. It's trained as a large language model of kind of a bit of everything, but they can tune them, these AIs, to do mathematics and so on, you know, and have add-ons, and that's where it's beginning to get interesting and will be in the near future, I'm sure. So keep an eye on this. Thanks.